Okay, so we're happy to have Gioele Zardini screen sharing, talking to us about co-design of complex systems. And take it away, Gioele.
Okay, thank you very much, David. Somehow we miserably failed the experiment, I guess. You can hear me, right? Yes. Nice. Thank you very much for inviting me. It's an immense pleasure to be here. To be honest, I've been a huge fan of these seminars, both the Berkeley seminars, the Topos colloquia, actually everything Topos does. And I'm very happy to be here. Two disclaimers. I'm not a mathematician, I'm an engineer. And so I hope you will be patient with me if I'm sloppy on some things, hopefully not. And the second is that I will talk about co-design of complex systems, as David said. And the goal for today is really to get to share my vision for where I want this to go. And it's possible that I will open more problems than the one I will close. And the best outcome for this is that we sit down together at some point and discuss what interests you about all of these things, and maybe we get to work together. All right, so let's get started. What do I mean when I say complex systems? Well, I started thinking about complex systems in my past when I was working on autonomy. So autonomous systems are taken in this talk as a proxy for complex systems. And I think about these systems for them to have a positive societal impact, right? So you could think of it in terms of autonomy for safer and efficient mobility. You could also think about autonomous robots to explore new spaces, such as space. You can think about robots to monitor environments, or you can also think about search and rescue tasks. In general, whenever you are thinking about these systems in a societal context, you need to think not only about their design in a lab, but you really need to think about the joint design of the technologies together with the environment in which they are embedded, right? This is very simple to think about. If you think about mobility systems, one thing is designing an autonomous vehicle in a lab. One thing is to put it into a societal context where there are interactions, there are impacts, and so on. And in this context, there is always the two sides of the medal. There is the heaven and hell, right? On the heaven side, for instance, autonomy promises to reduce the number of cars you actually need, promises to make public transit more attractive, more affordable, and sustainable. On the other hand, though, we know that when we implement these technologies in a suboptimal way, this might increase congestion, this might increase power consumption, and so things might also go bad, right? The bottom line, or the motto for my research, is that we understand slowly how to understand single components. So we know how to design them, but we still lack a tool which is both formal but also practical, which allows us to task-driven co-design complex systems. So really, this is what I'm up to, what my group at MIT will start doing in a few months. And this talk will focus a bit more on the vision I have for this. Then I will talk about some tools to solve the complexities that arise in this context. One is a tool called co-design, a monotone theory in co-design. And I will also touch base on some interesting aspects in strategic interactions. All of what I'm talking about, you can find on my webpage. There are pointers to papers, and I'm very happy to discuss offline if you are really interested about specific aspects. So really, let's get started. First of all, what do I mean with co-design? Topos colloquia are open to many different domains. And so I want to clarify what do I mean by co-design, because this is a kind of an overloaded term. Co-design, I see this really as a process through which we try to minimize some resource consumption in the context of satisfying some functionality constraints. You can think about resources as things like power consumption, money, but also errors with respect to a mission or some externalities you want to minimize. And functionality constraints are any kind of desired behavior for the systems you care about. And somehow we want to create a tool that helps the designer or the designers automate this process. So we want to have something in which you can specify a task, specify some multi-domain knowledge, and specify some design options. And then we want some magic to happen and some optimal designs to pop out, and even better, some trade-offs so that people can reason about the complex designs. So to be concrete, think about designing an autonomous vehicle. You could think about specifying the particular tasks, the scenarios the vehicle has to encounter, robot autonomy and physics principles. And here, the things you want to design are the components or the algorithms. and you want some magic to happen and now have trade-offs in terms of different design decisions, in terms of the errors with respect to the missions you had, and maybe energy consumption of the vehicle. In a very similar way, I could think about a mobility system co-design. Here, the task could be the demand and the differences between all the habits of people willing to move from certain origin to certain destinations. The principles are networks, operations, and infrastructure. And here, the actual things you want to design are mobility services and policies. And here, maybe one interesting trade-off could be the performance of the system versus the money that you have to put in. Now, why is it hard in practice to come up with this magic, with this thing that happens in the background? Well, there are at least 3 reasons. The first one is that whenever you have to design such a system, you have to make decisions at various levels of abstraction, and this requires different disciplines in the first place, right? Imagine designing a fleet of autonomous vehicles. Here you have to think about control, localization, sensing, perception, and some things are on the hardware side, some things are on the software side, some things are a bit in between, you have liability regulations. And so the first reaction as an engineer is to say, oh my God, there are too many components. It's very hard to make decisions. And also, we are afraid of making choices because we don't know where these choices are going to end up in the system, right? So we don't know the effect of these choices. And so the diagnosis in this picture of a therapy session is that we lack something which is formal, quantitative, but also intellectually tractable. Now, the second complexity is that not only we have many components that are interconnected, so this is kind of horizontal composition, but also we have some sort of hierarchical composition or vertical composition. Here we have whenever we are designing these systems, we have different levels. We can think about designing sensors for an autonomous vehicle. This is complex, but then we can put together many components inside the system, let's say an autonomous vehicle, and we have to choose the components for a particular setup. Then you have to put many vehicles together inside a service and operate this service. And finally, you have to put many services inside the urban ecosystem, for instance, and you have to make sure that these services interact. So you see, you have many components and many hierarchies. And the final complexity arises from the fact that typically designing these systems cannot be achieved by a single entity. Some problems require just a company to focus on a complex design, but sometimes you really require multiple stakeholders. Imagine designing a mobility system in Boston, in the Boston area. It's not only about technology or academia in this sense, because I come from academia, but it's also mobility providers, liability companies, policymakers, and industry. And these people not only reason very differently about the very same problems, but also they care about different objectives. So you're not always aligned in terms of the objectives you want to obtain. So to kind of summarize, I identified 2 big challenges. One is that we have large systems with many components, different scales, heterogeneous natures, multiple objectives, different languages, and so on. And the other one is that sometimes there are strategic interactions governing these systems, where you have many agents, heterogeneous interactions, and conflicts of collaboration. Now, if you want to design a tool that deals with all of this, those are the 6 golden rules that I believe should be fulfilled. And I believe that people in applied category theory really could resonate with those, right? The first one is that we need something which is formal and domain independent, right? To be able to bring together fields that speak different languages, you need something which is formal, but also something that's not specified to a particular domain. Typically, orthogonal to this comes also something which is computationally tractable. We want to solve problems in an efficient way. We want something which is by nature compositional in the horizontal sense, but also hierarchical, so we can consider different abstraction levels. It also needs to be collaborative and intellectually tractable, in the sense that collaborative, we want to pool knowledge from different experts, and intellectually tractable in the sense that we don't want this principle that only a system architect understands the whole system, but we want a more distributed design exercise. And finally, it has to be continuous. We need to be able to continuously change the design exercise. So the first level of complexity will be addressed by presenting some tools from a theory of co-design. And then I will touch base on the challenges for the strategic interactions part. So what I'm about to present is a framework that you might be familiar with, because some folks came up with it and advertised it, I think, in past years. I want to present a tool for co-design, where co here stands for compositional, computational, collaborative, continuous. And the idea is that it is designed to work across fields and scales, and leverages some principles in domain theory, applied category theory, and optimization. So the roadmap for the next few slides is that I will define what design problems are, how to model constraints between these problems, and how to solve these problems, right? So by the end of this first part of the talk, you will understand what these particular wiring diagrams that you see in my papers mean, in here, for instance, for the co-design of an autonomous drone, and how to actually make use of those to design some practical systems by optimizing for certain tasks, okay? Now, technically, this talk could be given without notions of domain theory and applied category theory, but since I know you guys love those things, it's your bread and butter, I will put an emphasis on those. I'm very excited that we are trying to teach these concepts to engineers in a book that's coming along, and I would love to hear your feedback about this. And also, these things exist since before, right? If you are interested about a compact yet very exciting explanation of this, I'm advertising that there is chapter, I think, 4 of David and Brendan's book that really presents co-design. All right, so the key to understand this toolbox is to think about design in terms of 3 spaces. Essentially, there is the implementation space, which is the things you want to design, the options you choose from. Those typically exist because they provide a functionality, a desired behavior, and typically providing this functionality comes at a cost or a requirement. Now, depending on the field you're from, you might know these spaces with different names. You know, functionality could be desired behaviors, specifications, objectives, guarantees, or conclusions, and the cost instead could be budget, requirements, dependencies, or assumptions. The key idea is that we want to be quantitative when talking about functionalities and resources. So we will model functionalities and resources using partially ordered sets. Partial ordered sets are useful because we can not only model preferences, totally ordered preferences, right? So things that are ordered in some lexicographic way, but also we can allow the uncomparability between certain elements, right? For instance, I could say that if I want to express my preference of where I want to listen to ACT talks, maybe ACT conferences is the best, and then I cannot say whether Topos, Colloquium, or Berkeley Seminar is the best. I actually like both, and I cannot really say. There are some cases in which one is good, some cases where the other is good. On a more serious note, in my research, we use partial orders, for instance, to express preferences over rules of the road. Here, for instance, you might care about collision energy, area evaluation, and clearance, but you don't really prefer area evaluation over clearance in terms of following a particular trajectory. And given this order on certain metrics of interest for trajectories, you can order the trajectories themselves, right? And you can have a motion planner use this knowledge to decide what's the best decision at any moment. If you are instead from information theory, you can think about a partial order of positive definite matrices. Here, it's very easy. You can represent these matrices by ellipsoids, and you can include, you can represent the order by the inclusion of these ellipsoids. Just to show you what kind of things we do with these partial orders that maybe you have seen in a very technical way so far, is, for instance, we can order sensors and algorithm pairs in the context of object detections for autonomous driving, right? Imagine you have a pair of a sensor and an algorithm, and you want to evaluate how the perception pipeline works. You can represent the quality of the detections by false positives, false negative, and accuracy rates. And this depends from the distance. The quality depends from the distance to the obstacles. Now you can order these curves by, for instance, dominance, and you can create partial orders here. The bottom line is that we will use partial orders to model these spaces. And while we care about implementations, the key question here is feasibility, right? So the key question we want to answer is, given a certain functionality or a certain desired behavior and a certain resource or a certain budget, does there exist a design in the list of designs I can choose from that provides at least the functionality I have by requiring at most the resources I have available, right? So this is a monotone map, in the sense that if I become less picky in functionalities, this should not require more resources. And on the other hand, if I suddenly am richer in resources, they will not provide less functionality. Technically, you can understand all of this as a Boolean profunctor. And we will represent this with this diagram where you have functionality as green wires on the left, and resources as dashed wires on the right. Okay. So the reason why I really like the concept of feasibility is that it is very flexible for us in engineering, because you can suddenly populate them in various ways, right? One way could be you have a catalog, you have designs that exist, and the same existence of a particular component, let's say a battery or a drone, gives you a relationship of feasibility between certain properties of this component. Sometimes you don't need catalogs. Sometimes you have things that are true from first principles, so to say. For instance, I can always say when I'm designing a drone that the energy required for the mission, it's always greater or equal than the duration of the mission times the power consumption of the drone. And that's true no matter which drone I look at. And I would argue that in practical applications for us in engineering, what's really important is the data-driven or on-demand population method. And here is one that only has a sequence of data points. And those could come from experiments, simulations, optimization problems, right? Whatever you use to, yeah?
May I ask you, can you explain how a catalog gives you a, sorry, for everyone in the audience, Gioele said that it's okay to interrupt with questions, so I'll do the first. Can you explain how a catalog is a Boolean profunctor?
Oh, yeah. Good question. Thank you, David. So a catalog, say that you have a catalog of different drones that relate, for instance, these quantities that you see here, the flight time, the top speed, and the range of the drone. Okay? Now, each different model of drones could be a different point in your catalog, in your Boolean profunctor, a different point in the feasibility relation that says, for instance, one could be a Spark drone that says, you know, I give you 16 minutes of flight time at 31 miles per hour, and I require $499, for instance. And that's a particular point in your feasibility relation.
Okay, and then you just say, and I can do anything less, I can do any less amount of flight time or any less amount of speed. And
for instance, yes.
A profunctor. Okay, thank you.
Yeah, for instance, yes. And the same goes for all the other methods. Now, I just want to convince you that this is not in theory land, and I hope when you go out today and look around you on the streets, you can draw some boxes like these ones and think about co-design, think about a Boolean profunctor in those terms, right? For instance, you can design an electric motor to be a relationship between speed, torque, cost, mass, and current. You could think about designing an autonomous vehicle in terms of the achievable speed with some guarantees of safety, for instance, and a particular set of tasks that you want your vehicle to do with respect to fixed cost and operational cost. You could think about as a system of systems. You know, you have drones that need to simultaneously cover some area to explore. And this requires the speed of each agent, the number of agents, the time needed to cover the area, and the cost. And you can think about designing a city in terms of a demand versus investments and externalities. But really here, I want you to think about anything. So you can think about other applications here. I'm focusing on mobility and autonomy. And the reason why we really like this is because not only it's clear what a single Boolean profunctor is, but there is a clear notion of how to interconnect them, right? So you can put them in series, you can put them in parallel, you can have feedback, you can be choosing between two options or trying to convince two experts, and every interconnection returns again something of the same kind, right? So there is a category where you can prove some properties. In particular, it's trace monoidal and locally posital. And this becomes a practical tool for engineers to decompose large problems into smaller sub-problems, okay? So, and also another thing maybe that's worth mentioning is that while we like all the math that's in the background, once you have these diagrams, it's very easy for engineers to just focus on the diagrams and interconnect them without worrying about what's happening in the background, right? So that's the beauty of it. So yes, it's formal and compositional and hierarchical by design. Now, what does it mean to solve these problems? Because so far I described those feasibility relations are design problems, but how do you solve them? So there is two notions of solutions. One is, given some functionality to be provided, how do you find the minimal resources for the implementations, the designs that minimize the resources? On the other hand is, given resources that are available, how can you maximize functionalities that you can get? So the two problems are dual. So for the narrative, I will just focus on one. And the particular question is, given an interconnection of designs, how can we find a map from functionalities to upper sets of feasible resources? This will be the red area here, or a map from functionalities to anti-chain of minimal resources, or Pareto fronts of minimal resources, okay? Which would be the points here. Now, if we frame this in terms of an optimization problem, this is a particular class of optimization problems that's specified by specifying a diagram or a graph where the nodes are these feasibility relations and the edges are the different interconnections between them. The variables of these optimization problems are the partial orders, functionalities and resources. And then you have two kinds of constraints. The first one is that for each node, you need them to be a design problem and have this component feasibility that we discussed before. And for each edge, wherever you see this symbol, you have this so-called co-design constraint that says that the resources required by a first problem should not exceed the functionalities provided by a second one. And if you think of this, makes a lot of sense in, for instance, physical terms. Imagine there is a process requiring some power. You can never exceed the power that's actually provided by another process, okay? And the objective here is to minimize the resources at the system level. So I want just to note that so far, I just specified the structure of those feasibility relations, how you can interconnect them, but I never said that those are convex, they are not differentiable, not continuous, and not even defined on continuous spaces. So those are properties that when you're solving optimization problems, you usually would like to see. We don't have those. But there is a nice story that tells you that you can solve this problem with a compositional approach, and you can find solutions to these problems. In particular, the starting point is that you know solution map, this ones I mentioned before, for each node of your problem, and your query is to find the solution map for the entire graph. And the kind of compositional solution we have is that you can solve the composition of problems by composing the solutions of problems. And now, probably when I explain this to engineering audiences, they look at me like I'm just playing with words, but I assume you guys really understand what I mean. In some sense, we have a functor between some notion of problems and some notion of solutions. And that's the key here. Now, I'm happy to discuss offline about the details, which discussing the algorithms and so on, it takes a lot of time. But I want to give you the gist of it. You can essentially find this functor, which simply means that given these solution maps and given the operators to interconnect the different design problems, you can find formulas to interconnect the solution maps. And this gives rise to an algorithm, which is a least fixed point algorithm, and it has two main properties. The first one is that we have a complete solution, meaning that we can find the set of all optimal solutions or a certificate of infeasibility if things are not feasible. And in the second important take-home message is that the solution is not combinatorial in the number of options, but just linear in the number of options. So this is great because we will have huge systems, right? You don't want these computations to explode. And the complexity actually depends on the interactions between different components. And so these interconnections, okay? So it is computationally tractable. And in particular, I'm happy to discuss offline the details, but in particular, the way you can formalize this is that you formalize a category of solutions. Essentially, we call pose U. This is a category that still has posets as objects, and morphisms are monotone maps of a particular form. And then you essentially can show that you have two functors related to the two queries I presented that give you essentially the solution maps for an interconnection of design problems. And I think here you can see this in a graph. You can start with a design problem, and you can have a functor that brings you to the category of solutions, and you have also the functors that go back, and you also can move in any direction in this diagram. Now, this is a Easter egg for later in the outlook for future work. There is an interesting question here, which is, what if we start thinking about enrichment of these functors in some performance space, for instance? That could be interesting to see whether you can choose multiple solution algorithms and which one is better than which other in some quantitative comparison. Okay, so the good news also is that people don't need to use this theoretical or developer viewpoint in practice. There is a company now launched by a collaborator of mine, Andrea Censi, the guy that initially came up with many of these things, that is designing a language and a solver to solve this problem. So right now you can literally think about any co-design problem you care about, and you can start using this language and starting using the solver, and you can solve the co-design problems without any issue, right? So this is not future work. This is something that exists, and we are using it in our work. And now I want to show you the kind of things we can do with it that we are doing in my group. So the typical thing you want to do when you start using this tool from the practical point of view is to define the particular task you care about. For instance, urban driving, right? The second thing you want to do is take this task of urban driving and decomposing the functionality into sub-functionalities. For instance, urban driving is following a trajectory and other things. And following a trajectory is a mix of lateral control, so tracking your path, and longitudinal control, which is both tracking some particular speed you want to go to, but also being able to brake in case of emergencies or obstacles, right? And you can go on and do this, this decomposition. By the way, an interesting question here could be how to come up automatically with these decompositions, right? Right now, assuming that you can do such a composition, what you then want to do is find the components of your systems, right? Now, when you look at the diagrams, maybe you might be tempted of thinking that those are information flow or data flow diagrams. You know, in case of an autonomous vehicle, you have a sensor that produces data for an estimator, that produces data for a controller. Instead, here you should think about logical dependencies, right? Decision-making requires a state estimate that requires data, algorithms, and computation, that requires sensors, programmers, and a computer, and so on, right? So this is the way to look at these diagrams. Once you found all the components, what you want to do is find common resources and bring them together, somehow account for their merging, for instance, sum. And those typically in autonomy are size, cost, weight, power, and computation. So you might wonder, okay, but where is the feedback? Where are these co-design constraints you talk about that are very hard to solve? I have essentially two interpretations. One is a physical one. If you're designing a drone, this drone requires actuators to move. The actuators themselves require a battery to be powered, and the battery must be carried by the drone. So the more power you require, the more actuation you require. But the more actuation you require, the more power you require, right? So this is a irreducible complexity of this design. But you can think of these also in systems that are not necessarily have to do with physical quantities, right? You can think of it as a component must be, you might be able to buy the components, then you should have these components produce a behavior that justifies the cost, and then the components must support this behavior, and you have this eternal feedback loop between an engineering problem and a business scale or a societal impact of this engineering problem. I think now an interesting aspect is that when you want to do these things in reality, the first thing you should do is write your diagram. So write your co-design diagram and interconnections, and forget about how you will actually populate them, right? You want to identify what the components of your system are, what the quantities of interest are, but you don't want to care about the particular methods you will use to populate your feasibility relation. And here, of course, the context informs the level of detail. Depending on who the problem is interesting to, you might think of designing an autonomous vehicle as a relationship between some speed and some costs. But instead, if you are an engineer at Waymo, let's say, one of the big autonomous driving companies, you might care about a very granular definition of this feasibility relation, where you take into account speed, particular tasks, the environments, the distribution of possible things that can happen, as well as safety and discomfort metrics. The second thing you want to do is populate these models. Now, you can populate them in the different methods I presented before. And the very exciting thing for me is that I want to tell you about these three key features of these population mechanisms. First one is sometimes you are unsure about certain components. And with this approach, it's very easy to embed assumptions. You can say, I'm assuming I don't know anything about this other component, and I'm assuming the worst. I'm assuming it will behave very badly. You can do that. Or you can say, I know an engineer that's working on that. It's my friend. I trust what he does, and it's going to work very well. And anything in between, right? You don't have to think. The second thing is that you don't have to think about this design exercise as something that's only for the current times. You can think about predictions for the future. We are now working with companies that might want to design a certain component and are asking the question, let's say I produce this component with these properties, will it change the state of the art? Yes or no? And so you can start looking at problems that are parametric with time. And the second thing is that although we did all of this in the same lab, TTH Zurich, actually, you can think of this as a decentralized process where different people contribute to different designs, and you have these humans in the loop thing that makes things interesting and opens up new problems. So yes, going back to the original queries, we have something which is continuous, collaborative, but also intellectually tractable. You just have to understand how these diagrams work. So I just want to show you that this thing is real. We are doing real things with real case studies in real world applications. For the kind of functionality, the composition I presented before, you can come up with this design diagram where you have different blocks for the different pieces. And depending on the domain the pieces are originating from, you can use simulations or solving optimization problems to populate them, or you can just create catalogs out of existing components, or you can take state-of-the-art research, for instance, in perception, that have some benchmarks and upload them into the feasibility relation population. The cool thing you can do is that once you have such a diagram and you have populated it, you can query it for certain tasks. In this case, we are designing an autonomous vehicle based on certain simple tasks. Imagine that you fix a certain urban environment, you take realistic roads, all the measures and so on, and then you fix a task. For instance, the task of switching a lane at a certain speed with a certain curvature. And now you can suddenly query the optimization framework to find you the optimal designs that minimize the error with respect to the original mission, to the original trajectory you should follow, and the cost of your system. Here you see that you find a number of these optimal solutions that are not comparable. And for each one, you can actually know the particular details about the autonomy stack. So which controller, which sensors, which parameters, and so on. And it's very easy to change task. Here, for instance, I'm taking a strong curve and also change the resources you care about. For instance, here I'm adding also control effort versus control error. I think the monotonicity aspect of this is well visualized in this plot. Imagine that I characterize the complexity of my task as a trade-off between the curvature of the curve and the speed of my vehicle. You see that essentially if I move right or top right, I'm making the task more complex and I will require more and more resources, okay? Nice. So now I want to take a step back and actually go back to the original societal problems I set up, right? I don't see these, of course, I see these as something that can be applied for engineering problems for specific companies that want to design a single platform. This is a great case study and we are doing that. But really the way I see this is something that can be used for different stakeholders with totally different backgrounds to talk to each other and design together some systems. So here I take the perspective now of a municipality that wants to make decisions about technologies or mobility solutions. Imagine choosing the number of vehicles you should allow in your city, how should you modify infrastructure, how performant should the vehicles be, how should you design your incentives, and so on. Again, this is a similar problem, right? We have some task, which is the demand you want to satisfy, or the projection of this demand. And then you have some mobility solutions and network that you want to co-design. And here it's not anymore people from different domains in autonomy, so a very specific domain, but it's transportation people, autonomy, economics, policymaking, very different folks. Now, the cool thing is that you have these hierarchical compositions. So you can suddenly think, you can take the co-design of a single vehicle and think about now an intermodal network when you want to design a service of autonomous vehicles for a city, a service of micromobility operations, and some trains. And in the years, we did various case studies with different levels of granularity. and now I want to present you one of those, you can essentially come up with a co-design problem that models this as designing the autonomous vehicle fleet, micromobility options, the public transit option, and the orchestration of all of these systems, right? And in the very same way, you can fix some demand patterns. For instance, in Washington, D.C., we have been working with the data from those authorities. You can, for instance, say, I fix a certain demand pattern, and I want to minimize cost and the average travel time in the city, and you find a full set of solutions that inform you in this way. And now each solution is not anymore just the technology you're using for a particular vehicle, but it's also how many vehicles, how many e-scooters, with which frequency should the train be operated, and so on. And I believe that this kind of trade-offs is what people sitting at this table really need to make decisions, rather than sometimes, you know, in engineering, there is this thing of providing a single solution to stakeholders, and that's not really non-transparent. I want them to be able to play with parameters, to play with these trade-offs, and understand what are the different factors to consider. Now, this brings me to the second piece of complexities. When you look at these kind of problems, it's pretty obvious that assuming that you can design all of the system and pretending that people will comply with whatever design you create, it does not really work in practice. You cannot assume a dictatorship like that everywhere, right? So what you really should think about is these notions that I presented, but in the multi-agent setting. So instead of thinking about optimal designs, we should switch towards thinking about equilibria of designs or interactions of different designs. And so one thing I want to do in the next years is come up with a more practical theory of co-design games. So imagine that you now misalign some objectives, and some of these blocks belong to different people. How do you model this thing? In this spirit, I did two works so far that contribute to the problem. One is that we realized that these feasibility relations and partial orders are very important to model these interactions between designs. And the first step is to actually model games in which these cost structures appear, which is something new. And the second is that there are some interactions happening at a hierarchical level. And so I'm working on solving some games that work at this, that happen at this, with this hierarchical scheme. Now, in the interest of time, and also I think this first piece is more interesting to this audience, I will just talk about the first one, but I'm happy to discuss the other one offline. So here, the starting point is that we want to be able to solve interaction problems where people specify their behavior in a partially ordered way, or by essentially specifying a hierarchy of objectives. And this is very well targeted to the problem of behavior requirements for robotics, right? Imagine designing an autonomous vehicle. Here, you need to think about a number of things, you know, culture, functions, ethics, safety, liability, compliance to traffic rules, courtesy, comfort. There are so many things, and it's very difficult to think about a unique behavior model that takes into account all of them, right? And it's if you start by thinking what you would do in a human situation, so with human drivers, what you typically do is you certify the vehicles, you put in place some rules of the road, and then you enforce the rules. But rules are strange, right? A study of my advisor back in the days was showing that, for instance, in Switzerland, there is a fundamental norm that says all road users must behave in such a way not to pose an obstacle or a danger to other road users, which simply says, sure, it's important to not violate rules, but some rules are more important than others, right? So there is already this notion of hierarchy between rules. So the typical things people do in robotics is you put all rules or all things you don't want to happen as hard constraints, but this is not very useful in practice because you don't know how to deal with infeasibility. Imagine you have an autonomous vehicle that's driving in the center of San Francisco, and suddenly it has, it has 1,000 trajectories, and no trajectory is feasible. Every trajectory returns a red flag that says, no, unfeasible. What do? You cannot stop, right? You have to find a way to deal with infeasibility. And more importantly, from a technical perspective, when you start analyzing multi-agent scenarios, it's very hard to find guarantees for the behaviors that will emerge. There is a second line of work that simply tries to look at a case analysis And there is this, in the industry, there is this statement that says, if statements kill people, you will never be able to possibly characterize all the possible cases your system will encounter. And the other thing is just relax. Put everything you care about into a single cost function, and you're good with it. Train the values, the parameters that give importance to the different factors, and you're good to go. This is very bad because, first of all, you cannot make it work for every possible scenario you care about, but also it's not transparent. So if things happen, you don't know why they happen, and it's very bad. So what should we do as researchers in this field? One could say, okay, but that's not our problem. This is like a policy-making problem. We should throw the ball at them, or we should try to incorporate our own beliefs in their algorithms. No, that's bad, right? What we want to do is create a transparent and customizable system, exactly as I explained for co-design, and engage with the stakeholders from the beginning. And in particular, the big mentality shift that happened some years ago was the idea to consider minimum violation planning. So this idea that you will violate constraints, but you just want to find constraints that are least violated, okay? So the first efforts in this area was to create a total order of different realizations. For instance, a taxi cares about safety, compliance, comfort, and performance. A race car instead cares about compliance, performance, safety, and comfort, right? And different users might care about a different priority. And this was very practical because it allows a modular definition of behaviors. It is very easy to predict what the car will do, but it's also easy to understand why the car did something. But in all of this, we were not able to consider uncomparable rules, which are present in today's systems, right? Sometimes you cannot tell whether you prefer one thing or the other. So one thing that was introduced is this notion of rule books that represent rules of the roads in partial orders, exactly as I presented before in this toy example. And it was shown that you can use this tool in the context of motion planning for robots, in which you want to find good trajectories. And the best way to get good trajectories or good ideas is to get a lot of ideas and then be able to throw away the bad ones. So you have some sort of creativity and good taste. In practice, what this means is that you have the autonomy stack of a vehicle in which you produce observations of the world through the perception, to the sensors. The perception says what's the world state, and then you have a planner that needs to tell you what to do. There is a piece which is creativity, which is proposing trajectories, and there's a piece which is good taste, which is scorers, and in this case, these partial orders. So the practical take-home message here is that there was a company that was implementing these partial orders and was essentially showing that for different countries, you just need about 200 rules with 20 rule groups. And you can implement this, and this runs in vehicles that work every day. But now, how does it work when you have multiple agents? So the simple questions we wanted to answer was, okay, let's say now we consider a game, right? So a setup in which each player has a scalar utility function. Based on these preferences, they select an action, and then based on the joint actions profiles, you have an outcome, and then you want to study equilibria. What happens if you switch the scalar utility function into a partially ordered preference? And in particular, we looked at this in the case in which you have different vehicles with different preferences interacting and choosing their trajectories. So long story short is we were able to show that these kind of games can be written as potential games. So you can so you can provide sufficient conditions for the existence of equilibria. And also, now that you have this notion of orders, it's very easy to characterize the efficiency of different equilibria. And it's very easy to think about refinement or adding edges to your partial order in case you learn more about your adversaries. So this is very exciting work that, again, leverages these compositional structures in the back. Now, I want to spend a few seconds just before giving stage to questions to show what I want to do next. And next, essentially, I want to work on three pillars. One is, as you might have thought, is modeling and algorithmic foundations for these problems. The second is societal applications, and finally is user-friendly tools. So as you can imagine, this is a very new field in engineering, this co-design of complex systems. And there are a lot of things to be done, from the modeling, solution algorithms, to take things that already exist and bring them under the same umbrella, to exactly going and defining these co-design games. Here I brought some examples that I think might be interesting to you. So the first one is that right now, the way you use this tool is that we define some co-design diagram, we populate the models based on some specification, and we solve the problem. However, many times when you populate these models, you actually need to run experiments, run a simulation, solve an optimization problem, go and ask someone about some information. And how do you do that in a computationally efficient manner? Right now we are doing it a priori without any information of why we are doing it. It would be nice to have some sort of closed loop system in which we optimize the choice of implementation and the number of these implementations, right? So in some sense, we want to make this application-aware population of co-design problems. Another interesting bit is the idea of leveraging also negative design problems. So not only feasibility relations, but also infeasibility relations. This is something we started doing in recent years. We have a paper out in ACT 1 year ago, and now one preprint right now following up, where we actually model the negative side of things. And it would be nice to see how to embed this into the current system that we are coming up with. There is another piece of interest here, which is so far the functionalities and resources are atemporal and aspatial, right? We are not considering them explicitly in space-time. What if we were to consider them in space-time explicitly? This would be to give rise to a feasibility relation. You now would need a dynamical system that describes what happens in any mode, right? But that could unlock a new class of problems, for instance, supply chain optimization or motion planning problems, right? And here I have some initial explorations with a student that is visiting my group. We started seeing that there are some connections to Poly, but it's very early stages. But I have the gut feeling that this could be interesting to you guys to look at. Then another interesting thing is, how do you think about the design problem itself, the design process? Like, sure, we have these diagrams, but how should we have these diagrams deployed to the world and have people use them, right? How do you put humans in the loop? How do you consider these games, the interfaces? What's the right abstraction to think about different stakeholders from different domains? So there is a lot of work from the design perspective of things. There is also the last one, a lot of things to be done in uncertainty. How do you think about uncertainty in these problems? Right now, we have a notion of uncertainty, which is essentially upper and lower bounds. But how do you think about, for instance, distributions of feasibility relations and so on, right? And how does this new notion of uncertainty interconnect with all the compositional structures? Of course, what I showed you is mobility and autonomy, but that's not the only thing I care about. You know, I'm now working with aerospace company, automotive industries, energy design. You know, you can think about power grid optimization. So I'm really going out and evangelize about this, and I'm really looking for new applications. So if you come up with new ideas on how this can be useful, I would be happy to hear it. And finally, I believe that the key ingredient to the success of this will be to be able for people to be able to use it. And when I say people, I don't mean us or people in only the technology domain. I really want this to be applicable to everyone needing to make design decisions, right? And this requires a lot of interactions with these people, understanding what their issues are, what their languages are. And that's why we are holding a lot of workshops, literature, and classes. So if you go on with the one message is, designing today's complex systems is hard, and we need new tools to deal with them. I have some seed of tools that I'm using to do that, but there is a lot of work to be done. And in some of these systems, we require strategic interactions. These are some papers, but most importantly, I want to thank a number of collaborators, both students, but also senior ones. In particular, all the ACT work has been done a lot with Jonathan Laurent and Andrea Censi. And I also want to shamelessly advertise that I'm hiring. I will welcome visitors in my lab, hopefully many applied category theorists, and you can find more information on my webpage. And now I'm happy to answer any questions you might have.
Okay, thank you. Thank you, Gioele. Okay, so for questions, if you have questions, just raise your hand in the with the reactions button, or just unmute yourself, whichever you prefer. Let's see here. Got some claps in the chat here.
Oh, I see Kevin Carlson has
Yeah.
raised hand.
Kevin, go ahead. Yeah.
Hey, thanks, Gioele.
Oh, hi, Kevin.
Wow, lot going on. Hi. Really exciting stuff. I guess let me ask a little more about this connection to poly you say you started to hear. So this is with making adding the spatiotemporal component explicitly to your models. Do you want to just say a couple more sentences about how the spatiotemporality turned out with the liquid poly?
So first of all, when you consider spatiotemporal resources, everything extends. Like the queries, for instance, become spatiotemporal queries. They are richer, right? For instance, you can say, instead of saying, how do I get this desired behavior right now, you could think about any sort of signal in time, but also you can think about accumulating quantities over time, like how do I get this number of functionalities by this time? Or you have a very richer notion of queries. And now to be able to solve these queries, you could think of populating each feasibility relation in the old school ways I presented, but this would be very inefficient because somehow you have to explore all the possible dynamic interactions between them. Rather, you should think about the dynamical systems governing these problems. And it seems to me that poly gives you a very compact way to define mode-dependent dynamical systems, right? So maybe it's a very lame application of poly. Poly could do many more things, right? But right now we are looking at the right abstraction to characterize all of these problems, and poly seem to me that could give an elegant way to showcase this. But as I said, there is a student, Marius Furter, that's the guy mainly working on this. He's going to visit my lab starting from September for a couple of months. And hopefully by then we will be able to tell you more about this stuff. But happy to be in the loop if you have ideas.
Yeah, really cool. Thank you.
Okay, thanks, Kevin.
Thank you.
And Valeria?
Oh, hi, Joel. I was
Valeria.
I was going to the other side of the same slide because I saw this business of modeling choices in linear logic, and I was kind of wondering what sort of I mean, there is this paper that you mentioned, right, called Modeling Choices in Co-Design. And can you give me a bit more of a mathematics of which choice is that? Are we talking co-products? Are we talking, what exceptions?
Yeah, there is, that's a very good question. So the choice, the work we did was very exploratory so far, but the idea is that, for instance, you want to be able to say, this resource is required, but who decides what the resource is? For instance, is it internal choice or external choice? These are some simple things, right? And so you might, this connects to the game theoretic aspects of them, right? Because, for instance, in certain cases, if somebody else is deciding, you can think about what in game theory is called security strategies, or trying to be robust to whatever they might do to you. Or in some cases, you are actually the leader yourself and you can decide. One thing we would like to do is come up with actually a student of mine, Eugene, worked for a while in trying to bring all the linear logic connectives into the co-design interpretation and understand how this works. We are not done with that yet, but it could be interesting to see what other new problems this would unlock, right?
Absolutely. Very, very interesting. People don't talk much about the two different kinds of ors in linear logic, but you look like you need them, right, for this business of who's deciding.
Yeah, at least I think, exactly, at least for the game theoretic interpretation, I think it would help a lot formalizing it, right? Because a pitfall I see now when we are trying to come up with this theory is that we will design something, but it will be a gigantic theory, very complicated. And right now, instead, I'm very happy that the co-design stuff is clear, right? If I am presenting it to an applied category theories, there is a category DP, there is a category of solution, functor, over. Like, that's it. Like, we don't need anything else to understand, right? I would like to find a similar set of tools for the interactive bits.
Absolutely. Thank you. Thank you. Very
Thank you,
interesting,
Olivia.
as usual. Thank you.
Thank you. Looking forward to chatting more offline.
Me too.
Okay, any other questions? If not, let's
Oh,
thanks for
Constantine has a
again.
question.
Who does? Oh, Constantine, yeah.
Constantine. Hey, Constantine, nice to see you again. Long time.
Hi, Gioele. So yeah, I had a couple of questions actually, but starting with these engineering variables that you're applying this thing to. There seem to be like power, energy, time, stuff like that. But I was wondering whether, there must be some physics involved. And is this, the physics equations, are they explicit or implicit in the modeling? So
Very good
somehow,
question.
power, energy over time and stuff, do you put in this by hand or?
So that's a very good question. Sometimes you have explicit constraints. Like imagine you're designing a drone, the power constraints should not exceed the power requirements. This can be enforced over time. This could be explicit, but sometimes some of these things are implicit in the population of the diagram. For instance, the orchestration of the mobility system is actually solving a very complex optimization problem where you're making sure that at each node there is flow conservation, that each edge you are considering congestion. So all of these you don't see because you just see the relationship between some properties of the system, these functionalities, resources, but in the background you have the enforcement of these properties. Another thing I wanted to say is it looks like we have only those quantities, but sometimes quantities are a bit more abstract. For instance, right now we are solving problems for autonomy design, where you have a motion planner, a sampling-based motion planner that is asking for queries in space, like is there an obstacle there with which probability? And this is a stream of resources. And then the perception system provides answers with other kinds of probabilities, like, yes, I think there is something there of this category, whatever. And those are other queries, and these two interconnect, right? So those are not quantities that you can usually classify with energy or these very simple quantities, but this is very flexible. You can really think of any sort of quantity that describes a system.
And I have one more question if there is time.
Yeah, go for it. Last question.
David is the boss here.
All right. So following up on Valeria's question there, so I was thinking, so I noticed a couple of, I don't know, modules that you had that were kind of adding stuff, like total, I don't know what it was, cost or weight or something like that. So it seems that you were adding also, not only comparing, so it was not only a partial order.
Yeah.
So already there, you would get T-norms and quantiles and stuff?
That's correct. Like the sum is a particular case of a design problem. For instance, if you're summing two things, you can think of the sum as a trivial design problem that takes two functionalities and returns one resource. And it's the map is a map of sum. But you could have anything in there, right? You could have a sort of discretization. You could have any other aggregation that you care about. And
so the question was, your functionalities and constraints, you define them as partial orders, but it seems that they are already quantiles.
Why do you mean so?
Because you were adding them, or you had operations on them.
Well, but wait, first of all, I might be adding, I don't know, monetary costs, and that's a total order. I get a total
That's a total,
cost.
yeah.
Yeah, but then I have other wires, for instance, power consumption. And even though power consumption is again a total order, the partial order, there is a partial order that is considering the product of these two total orders, right? So you in general, you can end up with partial orders.
I think the answer is that for any map of posets, there is a Boolean profunctor that does the same thing. Like for any functor between posets, there's a Boolean profunctor also, And since adding two real numbers or whatever is itself monotone, we can count it as a Boolean profunctor also. So
yeah, exactly.
Right.
That I agree, but I think Konstantin here is trying to ask whether are you asking something about minimality? Like I should have whether we could have used some other notion instead of partial orders?
I think he's saying if you have a monoidal poset where you can, where you can add two
okay.
things, how do you represent this? And you're just representing it as a map from that poset times itself to itself, right?
Yeah,
Something with two inputs and one output.
Right, you're right. Okay, yeah. David is better at getting this question, understanding what it was meant there.
I hope I understand.
Okay, thanks. I'll look up your reference.
Thank you, Konstantin. And yeah, I'm happy to chat offline if I'm interested in what cases you have in mind.
Yes. Okay.
Thanks all. That concludes today's colloquium. Thanks again, Gioele.
Thank you, everyone. Looking forward to catching up with the 3D versions of you.
Thank you. Thank you.